So now let's go to the second method to solve this problem, that is looking at the right hand side of the Stokes theorem. So on the right hand side of the Stokes theorem, remember we are talking about evaluating the integral between the vector field dot with dr, and dr represents here the line of the boundary of the surface. So basically you're not going to worry about this, you're just going to look at the line that connects this surface, and in this case it is going to be this circle over here. So this is my surface and this is the circle that I'm interested about if I look at the right hand side of the Stokes theorem. So here the equation that I will have is basically x squared plus y squared equals to 0, equals to a squared. Here, because my z is equals to 0. Okay, so now I will take v dot dr. So in this case, v dot dr is going to be 4y dx plus x dy plus 2z dz. So, and then I will have to integrate this equation, right? So here I will have v dot dr, and this is going to be 4y dx plus x dy, and then but then here my z is equals to 0, so I do not have a contribution from this term. In order to solve this now, we will have to change x and y into r and theta, and we use this equation that we are familiar with, that is x equals to r cos theta or phi. This is the azimuth angle, and y is equals to r sine theta. So from here, since r is constant, we are just changing the theta. So dx is now equals to a partial derivative of x with respect to theta, d theta, and this is going to be minus r sine theta d theta. Zy is going to be equals to r cos theta d theta. So now we are going to use this and we are going to insert it into here. So this is now going to be 4y is going to be r sine theta, and dx is going to be minus r sine theta d theta, plus this is x is r cos theta, dy is going to be r cos theta d theta, and here you will see that this is going to be minus 4, this is sine squared theta, right, and this is cos squared theta. So here's r squared cos squared theta d theta. So now you have to integrate this expression here. So I just remove this, and you can use the trigonometry function, to change this into either one of them, either sine or cos. Yeah. So let's say I change sine squared to cos squared. So this is going to be minus 4 r squared, 4 r squared 1 minus cos squared theta, and this is going to be plus r squared cos squared theta d theta, and this is minus 4r squared. This is going to be plus 4r squared cos squared theta plus cos squared theta d theta, and this is now negative 4r squared plus 5r squared. Okay, so there is r squared over here, and this is d theta integrating. So because the cos, let me see. Here, oh yeah, I missed something. Sorry. So this is r5r squared cos squared theta d theta. So now we still have a little bit more work to do. Here you have 4r squared, here you have 5r squared cos squared theta. Right, so let's remove this. And we will integrate this, but before that we will have to change cos squared into cos 2 theta, and here we will have minus 4r squared plus 5r squared, and this is 1 plus cos 2 theta over 2, and this is integration over the whole d theta. So now you integrate this over a limit where you go from 0 to 2 pi. So this is 0 to 2 pi here. And here you will have minus 4r squared theta, 0 to 2 pi. And you will have 5r squared over 2. And this is going to be theta plus sine 2 theta over 2, and you go from 0 to 2 pi. So continuing a little bit more, you will have 2 pi over here, so this is minus 4r squared 2 pi plus, so here you have 5r squared over 2, and here you have 2 pi as well. So here sine 4 pi is going to be 0, sine 0 is going to be 0, so you only have this term. So here you will cancel this, and then here you get minus 8r squared pi plus 5r squared pi, and the total will be a negative 3r squared pi. Right, so here r is basically the radius of the circle, so in this case the r is basically a, so you will have minus 3a squared pi. So here you get the same answer that you have from the first method, but in a more elaborated manner.